Good morning, afternoon, evening, wherever you are. My name's Robin Drogamuller and I'm chairing this session of the ICCCBE CIBW78 Joint Virtual Conference. So this session is on vision and image-based applications in construction of the ICCCBE Unmanned Aerial Systems Joint Virtual Conference. So this session is on vision and image-based applications. Right, sorry about that, getting feedback. Unmanned aerial systems, UAV, in construction and virtual reality for AEC. So we have 8 presentations in this session, if you have any questions to ask any of the presenters, if you can type them into the chat session at the side of the Facebook YouTube page, then they'll appear here for us to go through when we get to the Q&A session at the end of the first 4 or at the end of the second 4 papers. So please type in the number of the presentation so that we know who to direct the question to. Okay, so now I'll like to hand over to Shi Shen, who will be presenting on a real-time automated approach for ensuring proper use of personal protective equipment in construction sites. Thank you, Shi.
Oh, thank you. I'm Sutton. I'm with the University of Tokyo. So I'm here to introduce our real-time automated approach for PPU's identification. Okay, next slide, please. So here's the outline of my presentation today. First, I will briefly introduce the background scope of our work. Second, I will detail the methods we proposed. Third, I will introduce the experiments we performed and the results we obtained. And finally, I will give a brief conclusion of my presentation. So first, introduction. So construction work is much more dangerous than most other occupations where many potential hazards may occur. So in America, there were 1,008 construction fatal accidents in 2018, while in Japan, there were more than 900 construction fatalities during 2016 to 2018. Most of these fatalities could be prevented if the workers wore proper personal protective equipment, or so-called PPE, for example, like hard hat, safety glasses. However, actually, the workers do not precisely follow the construction site's safety regulations due to all kinds of reasons, even if they have been trained and educated. So an automated PPU's identification system is necessary. To this end, currently many works are being conducted, and they can be divided into 2 categories. First, sensor-based approach, which rely on physical tags or sensors employing PPE, like RFID, Bluetooth. But this advantage is obvious: the scaling cost or the real application of these sensors. So we have another option, vision-based approach, which are non-intrusive and require fewer devices because of the wide application of surveillance cameras in construction sites. And currently, deep learning-based object detection methods have shown remarkable performance on most visual tasks in the AEC industry. But current difficulties for the vision-based PPU's identification system are: first, multi-class non-PPU's identification; second, the performance on the viewpoint change and different individual postures of on-site works, which are actually very common in construction sites; and lastly, the real-time processing for the real application. So in response to this limitation, currently we are focusing on development of a novel approach to automatically identify any failure to wear PPE in construction sites. Of course, it will be a vision-based solution and to address multi-class NPU identification and be effective and robust with viewpoint change and different individual postures. Next, I will talk about how we achieved our scope. So the pipeline of our proposed approach is shown in this figure. So the images captured by on-site cameras are fed into our entity detection model. In contrast to the common used object detection-based approach, we provide a solution by the combination of object detection and individual detection. Then the NPU identification is performed using geometrical relationship analysis based on the detect PP and the detect individual to address the hard hats, masks, and visors in our current experiments. Okay, I'll give more details about our model. So first, for PP detection, we deploy the Euro model, which enjoys improved average precision for small objects. And the Euro 3 is a one-stage detection model, so it can be trained and trained to improve accuracy. And Euro 3 is really very fast, so it can be considered as a good option for real-time processing. Then for the individual detection, we employed a very popular and of course state-of-art human pose estimation model, OpenPose, which estimates 2D real-time multi-person key points using a two-branch multi-stage signal and outputs this kind of multi-person key points. Then for the NPU identification, for each pair of detect PP and individual, first we calculate a reference threshold based on distance between the detect individual's neck point and hip points. Then we calculate distance between detect PP and detect individual. If distance was smaller than the threshold, then PP is identified as being proper use, otherwise non-proper use. To further improve the robustness of NPU identification, we provide an alternative identification strategy in case of open pose detection failed at short distance. So this strategy considers only the object detection model is available and employed a human face bounding box to characterize the NPU identification. Next, I'm talking about our experiment results. So the target of our current experiments cover the three types: hard hats, masks, and visors. The purpose is to validate the performance of model under different conditions, say 1 meter, 3 meter, 5 meter. Also, different environmental conditions are taken into consideration. So to create the data set to train the object detection model, we collect this kind of 3D image from two sources, the web image and the real world image. And we labeled all this image and create data set with allowed 8,000 image, and using this data set to train the object detection model for PPE recognition. So after the model being trained, we perform experiments, and I will now show the results. First, the quantitative results under different distance for the hard hats, mask, and visors. So for the overall performance, our model achieved 84% precision and 93% recall, which demonstrate effective robustness of our model under different distance. And here are some identification samples. So under different distance and different color of rectangle refer to different type of detect PPE. And both like multi-person and single person and different condition. Also, we develop a real-time system which is able to run on around 8 FPS. So the demo can be seen here. There's 4 persons here, but 1 person is not wearing hard hat. So last risk was identified, as can be seen here. So finally, for the conclusion. So in this work, we have present a PPU identification system based on a combination of object detection and individual detection using geometrical relationship analysis to address multi-class NPU identification, including hard hats, masks, and visors. And in experiments, our model achieved high precision recall rate while ensure real-time performance under different conditions. So thank you again for your time. And in experiments, our model achieved high precision recall rate while ensure real-time performance under different conditions.
Okay.
So thank you again for your time. And in experiments, our model achieved high precision recall rate while.
Thank you, Chen, for that. So our next speaker is Wenji Q, presenting on image sensing based in building human demand estimation for installation of automated external defibrillators. So thank you, Wenji.
Hello. Good evening, everyone. Good evening, Chair. Good morning in Europe and good afternoon in Asia. I'm Wenxin Cho, and my advisor is Albert Chen. We're from National Taiwan University. Today, I'm going to share about a human demand estimation approach for the installation of AEDs. Next slide, please. This is the outline, and I would like to introduce it from the motivation to demonstrating our current results and contributions. AED is a medical device treating sudden cardiac arrest patients. And because of the location of AED is crucial to a timely access, it has been decided by mathematical programming models with an indoor passage network. So we want to estimate the human distribution on the nodes to serve as an essential input for those mathematical programming models. Sorry, next slide, please. To count the number of humans distributing in each spaces, such as rooms, we set sensing nodes at the entrances for placing sensors. Each sensing node counts the entering and leaving humans of the adjacent spaces. And from reviewing the current literature, we first clarify the required resolutions and find that the suitable sensor for our problem is RGB cameras. And methodologies of image sensing methods, including object detection, tracking, monocular depth estimation, and camera model can help us deal with the disadvantages of image sensing methods. So our objective is to construct a more automatical approach for counting humans in multiple spaces from a single camera. We take the image sequence recording the traveling of humans from existing surveillance cameras in the building. The other two inputs are camera parameters and sensing node locations. Our approach mainly consists of two parts. First is to extract information from the images, and the second part corresponds the information back to the real space. The first step is to detect and track humans in the image sequence. For each track, we only take the first location and the last location to represent the appearing and disappearing of the human. And we also put the RGB images into models to estimate the depth map. Now, having the points in image spaces, we first group them by clustering method. Then we match those clusters in image space to the real space by three approaches proposing different required camera parameters. The final output is shown as the graph on the upper left. When a human disappears from sensing area of a camera, it means that the human enters the adjacent room, so we +1 on the record. And if a human is leaving the adjacent room, it will show up on the image, so we -1. We use two real cases to validate our approach. One is at a corridor and the other is at a hallway. Both of them are at our school building, and one is 3 minutes, the other is 18 minutes. In the detection and tracking step, we see many track points that are actually not a human appearing or disappearing, showing white on the left figure. But we can filter them out by deleting those tracks that last for less than 1 second, meaning they are broken tracks. And the color on the image is the result of depth estimation. Blue means near to the camera and red means far. The color of the points are the ground truth that we label for checking if those points are assigned correctly in the final steps. On the left image, we see 2 points that are clustered to the wrong cluster. So they will make errors in the final steps. While on the right image, we see that the matching are all correct. This is a set of the final output. We see much error occurs at the entering or leaving time, like the red boxes. Because the lasting time for them are small, it do not largely affect the output of the value, but it means the camera will detect a human. The number on the right is the final output error. We test those cases with different detection and tracking models, frame rates, and some with a filter. The red boxes are best results of our output. And while if we use the most SEM settings, the error are consistent around 15%. The above is our current results. In this research, we make the procedure of assigning detect humans back to the real space automatically rather than manually circling the region of interest. Also, we use one camera to surveillance multiple spaces. In conclusion, our approach reaches less than 20% output error, and we found depth could be a feature for corresponding image space and the real space. Also, the approach could potentially support the input of AD location problem to serve as a demand. Next slide, please. This is my reference, and next slide, please. Thank you. And next slide, please.
Thank you, Wenjin. Our next speaker is Xiwan Zhu, who will be talking on vision-based pavement marking detection, a case study.
Thank you, Robbie. Yeah, hello everyone. Welcome to my presentation. My name is Shuyan Xu. I'm a PhD student in Curtin University, and the title for my research I'm going to present today is Vision-Based Pavement Marking Detection, a case study. So next slide, please. So a little bit background to start. So pavement markings are vital for the safety and order of the traffic system by providing efficient guidance and warnings to road users. They normally have standardized colors and preferably use long-life materials. So next slide. So among various types of pavement markings, line markings are vital. And this slide shows a few types of longitudinal line markings. And they are attached with their name, their illustrations in national manuals, and their images in real life. In addition, there are audio tactile markings on top of the ordinary line markings. And they are originally designed to provide audio and vibratory warnings to drivers who are drifting off the lane, so as to prevent collisions and increase traffic safety. And given the importance of pavement markings and the fact they are vulnerable to traffic wear, road agencies inspect and determine proper maintenance actions for them. And the as-is inventory data of pavement markings are the base of all types of asset management applications. So we have made clear the research problem about the inventory data collection of pavement markings using visual data. A group of previous work in the literature developed methods for detection of line markings and traffic lanes to assist the autonomous driving industry. And another group of study proposed vision-based methods to support digital asset management operations, including the detection, classification, and the condition evaluation of distresses that was found on the road pavement. So to be specific, for the first task, that is the detection task, it normally targets individual pavement damage, ranging from cracking, potholes, to blurry road markings. And in recent years, deep neural networks have gained heated attention and applied to this industrial field. And to further facilitate management operations, a few researchers managed to classify different types of pavement damage, such as crackings with different patterns, and the properties such as normal crackings and sealed crackings. And furthermore, based on the detection results, some researchers managed to evaluate the condition of road pavement by categorizing the damage status of targeted road into different levels. Also, the condition of audible markings can be quantified as well. So with regard to the needs in the industry and the literature review results, this study aims to develop a vision-based framework for pavement marking detection and classification so as to facilitate the as-is inventory data collection for the subsequent managerial operations. This slide shows the flowchart for the vision-based pavement marking detection framework. And it includes steps from image pre-processing, feature extraction, segmentation, and the final detection and classification of all types of line markings. So the first step is the image pre-processing. So image frames of road pavement are extracted from the videotape, cropped, and processed with smoothing algorithms. Also, an inverse perspective transform are applied to generate bird's-eye view images by manually selecting feature points for calculation. And then for feature extraction, a hybrid detector using a combination of color information, gradient magnitude, and gradient orientation was applied to generate the feature maps. And noises like shadows of roadside facilities can be efficiently eliminated. Then the segmentation algorithms are utilized to extract individual line markings on top of which detection and classification can be achieved. And in this case study, a threshold-based method was used for these tasks. Okay, this slide lists the performance of the proposed framework when applied on the case study. So for the classification of ordinary line markings, an average accuracy of 89 was achieved. As for the detection of audible markings, it achieved 82 accuracy for those located in the near field of the image space. So to discuss, we could see that there are detection loops due to a range of factors, including environmental noises, occlusions from other vehicles, and the warm condition of the identified markings themselves. So there could be improvements to the algorithms used in the framework. About the future work, more practical needs in the industry have been identified. For example, it would be beneficial to automatically quantify the warm condition of identified pavement markings, allowing managers to make informed decisions on maintenance actions like repainting. For another, other important properties of pavement markings, such as the reflectorization, that is, their ability of being seen in dark driving conditions, and the depth of those audible markings, and the methods based on image and video data for those inspection tasks would be beneficial for our road agencies. So that's all for my presentation. Thank you for listening. Agencies. So that's all for my presentation. Thank you for listening.
Thank you, Shu Yuan. Hope we can catch up in the near future when we're allowed to travel within Australia. Okay, so our final presentation in the first session is was going to be presented by Han Luo, but Peter is going to present in his place. So the title of this paper is A Vision-Based Pose Forecasting of Construction Equipment for Monitoring Construction Site Safety. So Peter, thank you for your presentation. Go for it.
Okay, hello everyone. So can you see my PPT now?
I can't hear you, Peter. Oh, sorry. Yes.
Oh yeah. So okay. So can you see my PPT now? Is it fine? Sorry. Sorry, Chair. Is it fine for my display?
Go ahead, put on presentation mode, please.
Okay. So hello everyone. So this is Peter Wong from the Hong Kong University of Science and Technology. So I'll be presenting our work about forecasting the pose of construction equipment for safety monitoring on construction sites. So basically, I'll go through introducing my motivation and the methodology we use, and then presenting the result of the experiment. So as we know, construction industry is quite a dangerous place with different accidents occurring, and particularly construction machines itself have the safety concern when it is staying, but it is still operating and maybe flying the arm to elsewhere. So this is important to track the pulse of machines. And currently, to do that, we rely on the human supervision mainly, which is labor intensive and error prone. Maybe one person cannot oversee the whole site and missing any accident, which will be serious. So we need automated motion tracking methodology. And particularly, we think computer vision is more useful than maybe some sensors to be installed, which may create very complicated installation issues. And particularly for current researchers on computer vision, we only can find the previous post but cannot forecast the future post. That's the question we hope to address. So that's the methodology we propose. First, we have a post estimation module to get the post of the equipment. And then we have the forecasting module utilizing a type of recurrent neural network, GRU, to predict the post in the next frame. So for the estimation module, we use a cascaded pyramid network, which is which was the state of the art for 2D post estimation. So we will use that model and to output the key points of the, let's say, excavator. We will output the key point and then jump into the next module. So the next module is a recurrent neural network. We particularly use this gated recurrent unit, GRU, which can outperform like the LSTM, and GRU requires less computational power and with high efficiency. And it can learn the sequential patterns over multiple frames and then to output the poses. So for training our model, we, based on key points, we input a sequence of previous poses, and then we output the next frame, the pose of the next frame. And the loss function, we follow the standard. We compute the L2 norm loss function and use the optimizer to do the optimization. For evaluation, we use these two evaluation metrics. So the normalized error, which is to quantify the error, the distance between the forecasted and the ground truth. And for the percentage of correct key points, we have estimate how many are correct given a threshold of the distance to recognize it as correct. And for the data set, we have labeled as we have extended the data set of some previous study by supplementing 6 key points as here. This is our previous journal work with the key points divided at the joint of the excavator. Then we label it for our training and testing. And particularly, we have 8,000 frames in total, and we isolate 80% for training and then the 10 and 10 for the validation and testing respectively. So that's the experimental setup basically. And for the loss, that's the result here. So it shows 2 curves. One is the training loss, one is the validation loss. So you can see both converging. So we can conclude that the model is performing at its best without like overfitting concern. So that's the normalized error. So as we have seen, we have 6 key points, and particularly it is good for the cap wound, which is like in the middle of the excavator body. But for the bucket, the end bucket, it is not that good compared with other key points. And similar patterns for another evaluation metric, the cap wound, the green curve achieved the almost 100% correctly with the very loose threshold. But for the other, the performance is slightly worse. And the overall discussion is that we think that the cap wound key points is usually visible on the videos, and with the movement is quite stable compared with others. While the bucket, because as the arm is moving, the motion is maybe occluded by the soil, by the stones, etc. So that gives the performance difference. So this is the qualitatively showing the XY coordinates over the time. So you can see the forecasted and the ground truth are quite similar. And particularly for the cap bone, there may be some fluctuation when it is staying over a period. So we think that it is because the GRU module may have some fluctuation or some accumulation of the error, because it is utilizing the knowledge from previous frame. So maybe the error somehow accumulate to give the fluctuation. So that we will be further investigating in the future. So to conclude, we utilize computer vision to forecast the process of equipment in the future. And we achieve quite an accuracy based on the evaluation metrics. And for the future work, we'll analyze the causes to the fluctuation result, and we hopefully can propose a better model in the future. So thank you all for the listening, for the time. Propose a better model in the future. So thank you all for the listening, for the time. Okay, so a bit delay, sorry.
Thank you. Thank you, Han. So that brings us to the end of the presentations. And we now have 10 minutes for questions. So that brings us to the end of the presentations. So if any of you have any questions, please type them into the comment section at the side of the web page, or the YouTube video page. And since I can't see any there yet, I'll start the ball rolling. So I'll start with Shi Shen. So with your system, how close are you with your development to actually using that on live construction sites?
Actually, we already have the real experiment in construction facilities, and with the real-time how system can run in real time and be useful for the PP properties execution. We already have real implementation.
Okay. Thank you.
Thank you.
And then a question for Wenji. With your placement or estimated placement of human defibrillators, have you compared the results of your system with the way human experts would decide where to place the defibrillators?
Okay, thank you for your question, Chair. For AD location problems, there are some literatures comparing the optimization models results and the humans results, and they can see their improvement on the retrieve time for getting an AED or the coverage for most of the people. Did I answer your question?
Thank you.
Thank you.
Right, so moving on to...
Did I answer your
Yes,
question?
no, that's fine, thank you. Moving on to Xu Wan. Thank you.
Thank you.
Right, so moving on to... So Xu Wan, with your system, you're using vision recognition to trace the lines in photographs. Once you've detected a line, does your algorithm then follow that line and use the knowledge you have about the position of a line to then follow that line in subsequent images?
For this stage, the detection is for individual image frames. It is not constant for the videotape, but I think we could use those previous knowledge to help with the detection in the next frames. And because this is a project and we are still processing and involve more algorithms, I think you provide a good suggestion. Thank you.
That's fine. Okay, so moving on to Peter. So with your analysis of the position of the equipment, my understanding is that you use that to then predict where, say, the arm of a machine or so on may go in order to cause a potential hazard to people on site. Have you considered how you would then use that information on site and inform someone on site that they're entering a potentially hazardous area?
So that is the extension work potentially. So we may think that there could be like extras, like the sensor maybe that if triggering the alert on the video, that can give an alarm to the workers nearby, and then yeah, if it predict that the arm is hitting a particular worker, and then give a alert to the people. But this may require another work is to track the workers as well. So that is what we will investigate further, how to combine the two sources of information.
Okay, thanks for that. Any more? Are there any questions from outside? Okay, thanks for that. Right. Any more? Are there any questions from? Okay, so we're not being inundated with questions from the audience at the moment. Okay. So I'll run through the four of you and ask how long do you think each of your technology will be before your technologies are available for use on live construction sites. So if we can start with Shi Sheng first.
Oh yeah, thank you. So our software already can be implemented for a real application, but currently we are like also focusing on development of our prototype hardware deployment, like compare the software, like also on-site IoT system and connect to the cameras. I think soon maybe it can be applied for the real application together with software. Thank you. Answer.
Okay, thank you. And when Jean, how long do you think before you're assuming you get funding and so on to continue the work? How long before your work might be alive?
Well, because my work has achieved a real camera on site, so I think the other works are to achieve multiple cameras so we can surveillance the whole building. And that's a problem about the error, to dealing with the error. So it will be soon to have a result. Thank you.
Yeah, thank you. Please exclude delays between you talking and me starting, because I've got a bit of a time delay. I'm getting the video on one stream and audio on another. So
thank you. Please exclude
delays. So Shiyuan, how soon do you see your stuff being used in real data gathering?
Yeah, so first of all, my application would be the operation and maintenance phases of road assets. And I think their application in the real life would be pretty soon, because the road agencies we are partnering right now have there's a bunch of image data of the road pavement, and we are currently developing a plugin for their internal systems to automatically collect those inventory data. And because for the operation stages, we don't need real-time detection or this kind of stuff. So I think the application will be pretty soon.
Okay, thank you. And moving on to Peter.
Okay, so for us, actually, we do have a real project, a real construction site, and they have some videos for us to test the algorithms. So we actually have already applied our algorithms to test in real site. Just that we may need further work in improving the accuracy. So you may have seen occlusion is one problem that we have been working on all the way. So maybe within several months or so, with one more publication that addressing the occlusion problem, maybe that will become the further enhance the usage in the real world.
And I would assume that you can also be doing work on a wider range of equipment as well, expand the range of capabilities.
Yes, yes. Sorry, did I miss your question, Chair?
Okay, righto. So I've run out of questions as well. There's about.
Did I miss your question, Chair?
You missed the question.
Okay, righto. So I've run out of questions as well. There's about. You missed the question. Okay, righto. So I've run out of questions as well. You missed the question.
I'm hearing myself over and over again. A few more, about 2 more minutes before the next presentation. So I'd like to thank the 4 of you for your presentations. Very interesting, and I look forward to reading more about your research as it progresses.
So I'd like to thank the 4 of you for your presentations. Very.
Okay, so if anyone's just joined us, ready for the next series of presentations, we've got another 2 minutes before that starts. Being a session chair in this format is good because there's no guarantee that no one's going to go well over time.
Hello, can you hear me?
Okay, so the first presentation in this next batch of papers is from Jiaoji Shen. I hope I pronounced that right. She'll be presenting on integrating UAV tilt photogrammetry and terrestrial laser scanning for 3-dimensional geometrical modeling, the post-earthquake country of Sichuan.
Yeah, thank you. Thank you for your very nice introduction. Hello, everyone. Good morning, good afternoon, and good evening. I'm Xiaoxi Chen from China. I'm a master student of Tongji University. And today I'd like to talk about how to integrate the unmanned aerial vehicles photogrammetry and terrestrial laser scanning for the 3-dimensional geometrical modeling of the post-earthquake. The earthquakes are considered as major disasters because they can destroy buildings and greatly affect human lives. Following an earthquake, to document the structural damage, time-consuming and dangerous human-led renaissance studies are conducted. However, such efforts are faced with many challenges. So therefore, to avoid these kind of challenges and acquire precise data in time, automatic techniques and advanced equipment should be used to inspect the post-earthquake building. So compared with current manual approaches, the UAV and 3D laser scanner can generate great higher quality data. And so the next part, the post-earthquake continent of Beichuan is our selected the study area because it witnessed the Wenchuan earthquake and retained both diversity type of the seismic damage of the buildings. So at present, it is reserved as an earthquake site for the purpose of the mooring and research. And this is our research can be divided into two parts. The firstly, UAV and 3D laser scanner were used to obtain the point cloud data of the roof and facade of the buildings. And then the two datasets were integrated together to generate a complete and precise 3D geometric model for the post-earthquake damage assessment. So first of all, a DJI UAV was used for the data acquisition. The flight took place at about 45 meters above the ground with appropriate parameters, and a double-grade flight path was executed to collect imagery. And totally 1,369 images of object area were collected. And these unordered overlapping images collected need to be processed to get point clouds. So in this step, structure from motion algorithms was used to recover same geometry. So by detecting key points of each image, the geometric relationship between image can be calculated. So in this research, images were processed by a commercially existing software called photoscan. So after image flirting, image georegistration, mesh refinement, and texturing, we can finally get the definitive point cloud and the triangular mesh of the object area. So in addition, a ferro laser scanner was used to make the scanning from different perspectives of the post-earthquake site. And in the step of preparation, the placement of the scanning station site was carefully planned, considering the building's locations, surroundings, and shapes. So what's more, to meet the requirement, each station need an amount of the overlap. So after scanning, we get 126 scans of the whole post-earthquake area, and but they have their own local coordinate system. So in order to express the entire object area, a coordinate conversion and combination process called registration was conducted. However, both UAV photogrammetry and terrestrial laser scanning methods have their limitations. Terrestrial laser scanning covers mainly side and inner information with higher density and accuracy, and UAV photogrammetry contains mainly roof information with realistic texture. So we integrate these two methods to generate a complete and precise 3D geometric model. So therefore, a course-defined integration method is proposed for these two techniques, and the method begins by manually extracting features points from the tails point clouds, and by back projecting these points onto the UA point clouds. Then after that, a refined transformation parameters are acquired by applying the iterative closest point algorithms. So finally, after registration, cleaning, flirting, we create high-density point cloud of the ground, collapsed buildings, damaged buildings, and other facilities in Beichuan County. Then the next is the three centers site was one of the most characteristic sites of Beichuan County. So in this paper, the 3D reconstruction of the three center sites was conducted based on the integration of these two datasets, and the results indicate that the 3D model was very quite of high quality and high precision. So in terms of seismic damage assessment, digital evaluation and also MASIC were processed by multi-resolution segmentation and classification. And then in further study, we attempt to establish the evaluation criteria of the different levels of the building damage to classify them. And since cracks are critical to judge the state of the buildings, we extracted wall cracks from high-density point clouds. And meanwhile, a damaged building was measured by calculating the normal vectors of the each plane. and these clearly reproduce the seismic damage observed in the field study. And Beichuan earthquake site is of great social and research values. However, structures of these buildings are constantly exposed to natural threats, such as flood, the rain. It's necessary to act to ensure its preservation over time. So therefore, yeah, that's our conclusions. Unmanned aerial vehicles, photogrammetry, and terrestrial laser scanners are used for 3D reconstruction of post-earthquake near Beichuan, and a method of the integration of two datasets is proposed to generate a complete and precise 3D geometric model. And our study also have some limitations, like because the result involves an enormous amount of data. So these high density data lead to be challenges with data post-processing and the software, hardware, and efficiency. And also the result may contains a lot of noise. And we still have a lot of work to do in the future. For example, we'll evaluate the accuracy of the different technologies and optimize 3D reconstruction algorithms and develop better noise removal method and build a 3D documentation system for the future study. Thank you for your attention.
Okay, thank you, Xiaoji. Okay, so the next presenter in the program, Xinjiang Liu, hasn't joined the conference, so we'll be moving along to a presentation from Judith Krishler on design principles affecting motivational and cognitive environments for VR learning environments and in engineering education. Thank you, Judith.
Thank you. Good morning to everyone. Yeah, my name is Judith. I'm a PhD student at the Bauhaus University of Weimar. And as you were saying, Mr. Drogemüller, I will talk about the design principles for a beneficial creation of the VR learning environment. Can I move the slides? Okay, thanks. I will talk about the motivation behind this paper, then also about an important psychological concept called the mental model, about the core of our paper, the design principles, and in the end about how to evaluate and to carry out the study that we are doing and give an outlook. Knowledge isn't everything, especially not in engineering. So the goal for us in teaching is to create for the learner the combination of knowledge and skills, which is called also in the literature a competence. So this is especially important for our engineering education. When it comes to an understanding of a topic, psychologists talk about the concept of a mental model. An advanced mental model can be equated with a very deep understanding of a topic, and the learner adds more and more information to his or her mental model and enriches it even more. So a coherent mental model, which is our aim in teaching, allows the student to turn and to rotate the topic in our head and to solve even more complex problems depending on how advanced this mental model in his or her brain is. Why do we want to use the VR to approach the mental model? There are many reasons, many benefits of VR, but one main concept we have to understand is that we want to go the way from the image perception to the mental model, which is a lot shorter than going over text surface perception, which involves heavy semantic and subsemantic processes for the brain. This is why we would like to use VR for that. So the way over image surfaces is the shorter one. Yeah, so when we are talking about which design principles are important for a good learning environment in order to create a very good mental model, is that we are talking about multimedia design principles. Thanks. Multimedia design principles. Those include different recommendations to support the learner while learning and facilitate cognitive learning processes. We have now, what you can see on this slide here is from our very early prototypes, where we were doing example for engineering education. What you can see in these pictures is one of the multimedia design principles involving annotations and labels. So we are putting in the VR environment, we are annotating information and giving additional information by using these labels and highlights. Also important, or very important, is the beneficial placement of these annotations and labels. We refer there to the spatial contiguity principle, which means we have to place corresponding elements, in this case the force, next to the equation where the force is put in, next to the explanation what the force means. We are putting that in spatial, next to each other, more or less, in order to make it easier for the learner. Last but not least, there is also the importance of strategic guidance. It can happen textual or verbally. And when it happens verbally, we call it auditory prompts. This is very beneficial because it creates the feeling for the learner not to get lost, let's call it like that. So it gives a feeling of safety in the learning environment. Why do we do that? We take all these principles into account to consider the cognitive load theory, so the load of the working memory. We have to keep the intrinsic and extraneous load low and the germane load high. What that means is that the intrinsic load refers to the content complexity and the element interactivity. So the complexity has to be kept low, and the extraneous load refers to the adequate design of a learning material. So when it's well designed, the extraneous load is low. The germane load refers to the active engagement with the learning material. The more active we engage with it, the better it is to understand and to process. Principles, we have created this configuration matrix, more or less, where we derive the different configurations for the testing scenarios. As you can see there are many of what I have just explained. So that is the configuration matrix we have created. And when it comes to the study, we do not only want to know how successful the learners were going through this VR learning environment. We also want to take a look on the motivational factors and the cognitive factors. That means we want to see how is the feeling of the person. So how is self-efficacy, fear of failure, anxiety in that learning environment, and also how high is the mental effort or the cognitive stress. That's what we are going to evaluate in pre and in post test. So before performing the environment and afterwards. For the prototypes, we developed them in Unity and Visual Studio and deployed it to VR glasses. So from this application we can derive the process data in order to support us in the evaluation process. These process data could be like false attempts, how many times did that person fail the task that was given, how much time did that person need, where was the attention guided, and so on. Yeah, that's what's going to be derived from the VR data, VR application. In the end, when we take now an outlook on where we stand and where we want to go, we are ready to start using the prototypes we have created for engineering teaching in the upcoming winter semester. Of course, everything got a little bit delayed due to COVID-19, but we have done the basic, all the research. We have created the learning scenarios, and have now all the tools to carry out the study next semester in our classroom. Okay, so far, thanks a lot for your attention.
Okay, thank you, Judith. Okay, that's going to be useful for us in some of the things that we're talking about doing here in Australia as well. Okay, now the previous presenter has joined us, so The next presenter will be Jingheng Liu, presenting on the scenario simulation of indoor post-earthquake fire rescue based on building information model and virtual reality. Thank you, Jingheng.
Yeah, thank you. Can you hear me? Okay, so here is the topic. Thank you for the chairman to introduce my topic. So let's go to the next page. Can we? Yeah, this is the outline of my presentation. And first, I will talking about the background of this research. Next page. Okay, so earthquake will result in the fire and the falling debris. Both firefighters and trapped people might face serious risks. Currently, we need to build a high-fidelity visual fire scenes that can offer a reliable training for the evacuation and rescue after for the post-earthquake fire. There's two problems. The first one is the combination of the multiple hazards that strongly affect each other. The second problem is the fire via scenario construction that need to take both realism and performance into consideration. Okay, next one. So here is the framework of our work. They have 5 modules. Modulus 1 is the beam transformation. Module 2 is the complete the model with the utility. Module 3 is perform the seismic damage assessment. Module 4 is carry out fire simulation, and Module 5 visualize the result. There is the sorry, what's wrong? I think this. The main method used of this problem is the multi-hazard analysis and via scenario construction based on utility. Next, we will introduce them in detail. Okay, next one. Okay, the earthquake will induce damage of sprinklers, which will aggregate the fire and the smoke. Ceiling will also suffer damage, leading to the falling debris on the floor. They both will strongly influence the rescue routine and the speed. Next one, okay. Next. Okay. Sprinklers and the ceilings are acceleration-sensitive components. Their damage are determined based on the time history analysis and the fragility curves from the FEMA P58. So here the figure shows how to define the damage to the sprinklers and the ceilings. Okay, next one. Okay, the seismic damage of sprinklers will reduce the spray flow, thus affecting the integration performance. The smoke will decrease the indoor visibility. The falling debris also collide with people, which will lead to reduce the moving speed of the people. The VR needs smoke visualization. There is 2 common approaches to visualize smokes. One is the volume rendering, and another is particle system. Both of them have their pros and cons. Thus, we combine them too. In the initial stage, we use the volume rendering, and at the spreading stage, we use the particle system. Okay. Next one. Okay. For the volume rendering, we output the source density from the fire simulation software FDS and calculate the transparency of this each grid. And for the particle system, we just adjust parameters and following the grid with this particle system. For example, there is a 400 cubic meter space. If we use random rendering, it will take 3 times of memory compared to the particle system, but the visualization is similar. So use this combination, we can save the memory and have higher performance. The case study is a 19-story hospital. It is a frame shear wall structure. We inputted commonly used geocentric ground motion and have the peak ground acceleration to 400 Gauss to simulate the seismic damage to the building. So after the calculation, we know that the maximum floor acceleration is on the 10th floor. and we assume that the fire is ignited on this floor. The results show that about 43% of the the ceilings were falling off, and the sprinklers in the ignited room are completely damaged. So if there is no damage in the sprinkler system, the smoke will be quickly controlled by the sprinkler. However, if because the sprinkler is damaged by the earthquake, the smoke will occupy most of the rooms and also the corridors in this story, Okay, next one. Okay, here it shows the detailed comparison. We can see that due to the earthquake damage to the sprinkler system, both the temperature, the salt density, and also the FED will be much higher than the one with no sprinkler damage. The difference is almost 23 times of the FED to the no damage case. So this shows the importance of the simulation sprinkler damage. Why it jumps so fast? Oh, okay. I don't know. Maybe a system problem that we don't see the. Okay. Okay, next one, please. Okay, thank you. No. Oh. No, next one. Next one. Next one. Okay, so here we show the fire scenario, a VR scenario of this post-earthquake fire. You can see that because the distribution of the smoke, that the visibility is much smaller, worse than the one without the fire simulation. Okay, so go to the next one. Okay. So we assume that someone is trapped in the one room on the story, and we construct 3 scenarios. The first one, we have no fire, no spring damage, no falling debris. And the other 2, we have the damage of the sprinkler, we have fire, and we can compare the result of these 3 cases. We can see that after having consideration the damage to the sprinkler system, there were more fire, and because the fire reduced the visibility, so that the electrical time will be much longer than the no fire and no sprinkler damage case. Here shows the detailed comparison of the 3 cases. And we also added 2 scenarios here that we don't consider the combination of the falling debris and the fire. We can see that they are different. Oh, sorry. Okay, so here comes conclusion that we construct a framework for the VR fire scenarios. And we can see that the falling debris and the fire after earthquake will seriously change the rescue time. And we have a new system framework to improve the performance. Okay, thank you.
Right. Okay, thank you, Xinjiang. Okay, our next presenter is Xiaozhou Wei, presenting on the integrated application of BIM and extended reality technology, a review, classification, and outlook. Right. Okay. Righto, he's out. Okay, can we then move along to the final presenter in this session, who was Ralph Taye, presenting on BIM GIS integration in HoloLens.
Hello, this is Ralph. I'm currently a PhD candidate at the University of Florida, and I'll be presenting this framework for the research I've been doing with Dr. Bademosi and Dr. Isa. So for the presentation, I'll be going over a quick introduction, a literature review on GIS and construction information systems, the interoperability between construction information systems, mainly BIM and GIS, and on some of the construction technologies that I'll be using in this research. Also, I'll be discussing the aim of the study, the methodology, and some of the expected results. We all know that the architecture, engineering, construction, and operations industry is known for its slow adoption rate of technologies. We've seen a lot of technologies recently being used in the construction industry, mainly building information modeling, GIS, and different visualization techniques, starting from 3D models on computer monitors all the way to virtual reality, augmented reality, and mixed reality. So considering the complex nature of the eco industry, it is really important to benefit from all the advancements that we're seeing currently in Industry 4.0 and use them to facilitate the evaluation and communication of all the information in the current construction projects. Some of these new technologies from Industry 4.0 are wearable technologies, and they're starting to gain attention in the construction industry. And then they can be used to better collaborate between project stakeholders and efficiently deliver construction projects. So just a quick introduction on geographic information system. GIS is a science and technology that relies on organizing data into georeferenced layers. It can basically be used for collecting, managing, and analyzing data. So traditionally, all these data were hosted offline on local files, then evolved into central databases hosted on servers, and then recently we've been seeing GIS models on online platforms or web GIS. GIS has been used virtually in a lot of fields. It can also be used as demonstrated in the literature in the construction industry in all its phases. Moving on to construction information systems and specifically BIM. BIM is also a database of information that you can use to visualize the construction project throughout the entirety of the life cycle. It enables a better control of the construction process since it minimizes information loss and it promotes better internal coordination, cross-disciplinary coordination, decision-making support, productivity improvement, and risk management. In the literature, there has been many studies that were centered around the idea of working with BIM and GIS together, especially that they are both related to databases of information. And there were different methods of integration that were discussed in the literature. The first one is extracting BIM data to GIS software. The second one is the other way around, extracting GIS data into BIM platforms. And then the third one is extracting the both sets of data into a third-party platform. This integration has been used in the literature in pre-construction, construction, and facility management. It has been proven to help decision makers visualize and analyze the building performance in the context of a broader enterprise. Some of the construction technologies that I discussed in the paper include AR. There has been many studies on AR, mainly the applications focused on mobile computing, coordination, communication, and visualization. Holography, on the other hand, and head-mounted mixed reality headsets such as HoloLens have been extensively used in the medical field, but their use in the eco industry is still at its infancy, since these technologies are relatively new. So the aim of this study is to evaluate these new technologies, specifically holographic applications of integrated BIM and GIS, and study how they can improve the learning experience of construction management students. So we'll be developing a new visualization method, and then we'll be evaluating the benefits of visualizing BIM and GIS in holographic environments and its impact on the spatial understanding and collaborative problem-solving skills of students. So the methodology started with a Delphi study between educators and industry professionals to see where they stand on the idea and on their prospects for the application of holography in the future. The development of the applications, it's starting in Revit and InfraWorks. The first is for BIM, the second is for GIS. And then the first tool that we're using is an interactive hologram that we previously developed in Unity that uses motion sensing. So we're using different scripts to export all the data. Similarly, to develop the application for the HoloLens, we are using Unity. We're evaluating both platforms, both tools for comfort, spatial mapping, and scale. The HoloLens application is tested on the emulator. And then once the applications are exported, we can use them as tools to test the effectiveness of holography to visualize BIM and GIS data together. Then the data is collected and analyzed. So I'm just going to share with you some of the initial results from the Delphi study. There has been a consensus among educators on the importance of including mixed reality technology, not just in VDC-related courses, but also in other construction management courses. Also, industry professionals focus on the necessity for schools to include mixed reality, BIM, and GIS in construction management education, and focusing more on these technologies considering the future of the industry. Some of the expected results, it is expected to be effective and easy to use, the platforms that we are going to develop. Also, since we are developing multiple plugins, we expect them to be useful for future research. And finally, the bulk of the research, we expect it to be beneficial for students and industry professionals to use holography and mixed reality headsets throughout the life cycle of the project. And we believe that the building holograms will enhance the user understanding of the models and allow them to make markups and communicate information more efficiently. Thank you.
Okay, thank you. I think the connection of our session chair, Dr. Robin, is out. Let's move back to paper 3A8, Mr. Shows Wu.
Hello everyone, I'm Shows Wu from MIT University. My topic is the integrated application of BIM and extended reality technology, the review, classification, and outlook. The next page.
You can go on, Shows.
Hello?
Okay. Shows.
Hi.
You can go on, please.
Sorry?
You can start your presentation.
Yeah, I already started my presentation. That's the slides. Frozen?
The slides on the screen.
Can you hear me?
Very bad connection.
Let me try again.
You can start, please.
Yes. Yeah, the architecture, engineering, and construction sector has been benefited from the continuous development of innovative information and visualization technologies such as building information modeling, virtual reality, augmented reality, and mixed reality. BIM is used to integrate and manage the building information throughout the project lifecycle. Apart from being extended reality merges the real world and the virtual world to allow a user to interact with virtual objects through actions. Here, BIM XR refers to the interaction of BIM and XR. Existing research about BIM XR have different research purposes and have led to a variety of outcomes. To understand the state of art of these research outcomes and identify the gaps and the challenges among them, applicated focused literary review, classification, and outlook has been conducted. Two common literature review databases were used to retrieve articles. Using the shown search method, 50 articles were going to be reviewed. Through the review, the application of BIM-XR can be divided into 4 categories. The first one is task guidance and the information retrieval. On-site individuals got their work from the managers through task list or by oral. They need to carry handbooks and the construction drawings to retrieve the building information to finish their work. All these traditional information transmitting methods are efficient and inaccurate. BIM-XR provides location-based context-aware method to extract information and tasks from BIM and display them by XR devices. The step-by-step instructions are presented to assist employees to accomplishing their work. The visualization and the interactivities of BIM-XR allow workers to review and refine a design effectively. The visual or auditory effects in an immersive VR scenario is similar to in the real world. In an MR or AR environment, buildings or building components to be reviewed can be superimposed on a real-world scenario, which enable a designer to review and refine the components on the spot while communicating with experts. BIM has been developing to adopt 4-dimensional scheduling and 5-dimensional cost planning, but it lacks a user-friendly interface with management functions. XR provides users with a programmable interface which can access the BIM models to check the construction activities, schedule, and the cost. By superimposing the virtual model on the real site, the difference between the actual process and the construction plan can be intuitively obtained, which also provides the potential to achieve digital twin concept. The last one is the upscaling of the AEC workforce. Based on the gamification, BIM-XR provides the immersive virtual scenario to improve the spatial cognition of trainees. The hand tracking technique allows users to do hands-on training in a virtual environment. It has been proven to be beneficial for upskilling. Through the review and the classification, we learned about the history and current status of BIM-XR. Based on the development trend of it, we can look forward to the future. In this section, we will discuss the development, architecture, and the applications. We found that the development architecture is increasingly focusing on interactive functions and the user interfaces. Therefore, a platform called Game Engine is increasingly being used to develop BIM-XR. In the game industry, the game engine for developing XR applications is well established. Using SAT, the client part delivers the location of its user to the server part. The server extracts the context-aware information from BIM and transmits it to the user. The architecture lowers the barrier to develop BIM-XR while providing interactive functions. As a technology that provides visualization and interaction for a single person, BIM-XR gives staff a virtuous cycle consisting of the training, assistance, and the feedback. VR training helps them understand their task in advance. AR or MR provides them with the detail they needed during the work. By setting up user account, personalized feedback will be provided to users for upskilling. Information in the server part should be updated in the whole life cycle of a building. Will consist 3 layers: build, maintenance, and demolish. Each layer can be divided by 4 quadrants based on the physical or digital, virtual reality or reality. Information flows in the quadrants and the layers. For example, to construct a building, the first part is designing it and making the construction plan. And then VR can be used to simulate the construction activities to ensure the implementation of the plan. And later, MR provides staff context-aware information to help them finishing their construction. After wrap-up, all the building information will be transmitted to the next layer. In conclusion, the research of BIM-XR will go in two directions. For individuals, researchers will focus on the development of human-computer interaction functions. For the industry, BIM-XR will apply to manage the building information throughout the life cycle of a building. Thank you. That's my reference list. Thank you.
Thank you. I guess our chair will be back very soon. He dropped it. Just a second. Okay, Robin is here. Hi, Robin. Go on.
Just come back in now.
Yeah.
Yep. Okay.
So now it's Q&A. Everyone has presented,
okay.
But Mr. Rolf is not here.
Yep. Okay. Thank you, Eduardo. Right, I dropped out for a little bit there, so that made life a little bit more difficult and interesting for me. Okay, we have some questions from the session. First off is a question for Shen. Basically saying, what is so special about modelling post-earthquake disasters compared to general modelling?
Yeah, can you hear? Thank you for your asking. The difference, I think, is that after the earthquake in the area is always massive and the seams are irregular. There are always a lot of rains, so it's not easy for us to get into the buildings or to around them because it's kind of dangerous. So we need to use some automated techniques to solve this problem and modeling. And also, I think after earthquake, modeling must need be quickly and of high precision because it's about the human lives and the building safety. That's my answer. Thank you.
Okay. Yeah. Thank you, Xiaoxi. Further question on that. With the work that you're doing, where do you see, or who do you see that would use the results of your modelling?
Okay, the result of the modeling, I think, right now is kind of fundamental because it's just about the 3-point clouds of the each buildings and the whole site. But how to apply this to the future study, it still need to be more further study. And I think the results now is kind of realistic and of high precision, but we still need the further study for the future. Thank you.
Right. Okay, so with the information you're gathering now, or the information you intend to gather in the long term with after future work, do you see that being used just after the disaster when you're going through assessing buildings to find out what work needs to be done? Or would you be able to gather information quickly enough so that it could be used during live rescue to assist the rescuers in assessing whether it was safe to move, say, a concrete slab?
Yeah, I think our research is right now is difficult to just apply it just after the disaster. because as I just said before, the thing is is massive and have a lot of rings, so it's a hard decision, a consideration for us to do our research. But I think if we train a lot of prospective people, it's possible. I think it's possible, and with the development of the techniques, it could be more faster and more automatic. It will be okay, I think.
Okay, thank you, Zhao. Next question for Judith. So with your the work that you're doing, do you intend using that to, say, explore alternative pathways if you can determine from the interaction that a student is catching on very quickly, or another student may be very slow and may need to follow an alternative sequence of experiments with the VR?
Yeah, that is actually planned, and we have discussed that in the research project, that depending on how much time the student needs, if we can see from the process data that that person is taking a lot of time to finish a task, to complete the task, or is failing many times, we could trigger that this strategic advice in order to the student not getting stuck. But we are right now doing that with the text label, so we are already doing it, but not with audio, because we have not implemented the audio part yet, but with the text guidance.
Okay, thank you for that. Right. Now, okay, so Ralph's no longer with us, so I can't ask him his question. And because I dropped out, unfortunately, I wasn't able to catch Xiaozi's presentation, so I haven't got any sensible questions I can ask you, Xiaozi. Yep. So are there any further questions from any members of the audience? Right. Okay. Well, we're not getting any further responses in the comments. So thank you all very much for your presentations. They were all very, very interesting. Fortunately for me, they align fairly well with some of the research and educational activities we're doing at our university. So thank you very much for that, and I look forward to reading and hearing about your research in the future. So thank you very much.
Thank you.
Thank you.